Hey guys, this is Professor Janacek, and I want to go over some examples where we discuss continuity. Let's start with example number 1 here. Is f of x equal to 3x squared plus 2x plus 1 over x minus 1? Is this continuous at 1? Well, if you remember the conditions for continuity, the first condition, I can write that a little larger. Here we go. Condition 1, we're looking for f of 1. In this case, our value is 1, so is f of 1, does this value exist? So let's see, what do we get if we evaluate f at 1? Oh, well, I see a problem there. We end up with, what is that, 6 over 0, and this is very much undefined. Which means condition 1 is not met. So the answer is no. F of x is not continuous at 1. Let's take a look at example number 2. Is g of x, the piecewise function, defined by x equal to sine of 1 over x for x not equal to 0, and g of x equal to 0 if x is equal to 0? Is that continuous at 0? Well, let's go through our conditions. Let's see, condition 1. What is g of 0? Well, that is our first, that is just our second piece of that piecewise function. G of 0 is 0, which means g of 0 exists. So condition 1 is met. How about condition 2? Condition 2 is that the limit as x approaches, in this case 0, of g of x, that also must exist. Well, what is the limit? Well, let's see. Now this is going to take a little doing. Since the sine function, and doesn't really matter what the argument is as long as that argument is defined, since the sine is bounded by 1 and negative 1, again remember this is for x not equal to 0, right? That would be undefined if x is 0. Since the sine function is bounded by negative 1 and 1, then we know that negative x is less than or equal to x times the sine of 1 over x, which is less than or equal to x as well. And again, this is where we're looking at getting closer to 0. And since the limit as x approaches 0 of negative x, that's equal to 0, and the limit as x approaches 0 of x, that's also equal to 0, then by the squeeze theorem, the limit as x approaches 0 of the stuff in the middle, sine of 1 over x, x times sine over 1 of x, is also equal to 0. So our limit, so notice again we're looking specifically at the condition when x is not equal to 0. We're just looking at it getting close to 0. So we want the limit as we get close to 0, but the fact that, so I don't even need to use this second piece on my function. I just want to get close to 0. I'm not really concerned at what happens at 0. So as we get close to 0, it looks like we're coming up with 0. So condition 2 is met. Again, because this also exists. And finally, condition 3, we need to see is the limit which in this case is equal to 0, is that equal to my function value? And it is. The limit as x approaches 0 of g of x is equal to g of 0. So condition 3 is met, which means the answer is yes. Our function is g of x is continuous at 0. Wonderful. All right, on to example 3. For which values of x is this function f of x equal to x over x squared minus 7x plus 12 continuous? So now we're looking at a collection of values. We're looking at an interval of values. Notice the first two examples we're looking at just continuity at a point. Now we're looking at it over intervals. Well, let's see here. I notice that f of x is a rational function, and thus it is continuous everywhere except when the denominator is 0. Remember, it's similar to polynomial functions. If I'm taking the limit of a rational function, I can simply evaluate that rational function at the limit value as long as I don't get a 0 in the denominator. So I want to look at the denominator. Since this denominator, x squared minus 7x plus 12, is equal to 0 when, of course, let's see, if we factor that, that's x minus 4 times x plus 3 is equal to 0. Which happens when x is equal to 4 or x is equal to negative 3. Then we can say that f of x is continuous everywhere except these two values, x equal to 4 and x equal to negative 3. Now notice, I do want to point out just real quickly, I'm using or here and there. This is, I'm using or here because I'm solving an equation and its solution, one or the other, makes it 0. But here I'm looking for places that it's continuous, and it's continuous at every place except this place and this place. So just watch the semantics there a bit. All right, here at the bottom of the page I do have some continuous functions. We know that polynomials are continuous everywhere. Again, that's how we take the limit of a polynomial function. Rational functions, as we just saw in example 3, they're continuous everywhere on their domain. Of course, their domain comes from when the denominator is equal to 0. That's how we limit what that domain is. We have radical expressions. Radical functions are continuous, but we do have to worry about a few things. So if n is an odd value, then it's continuous for all x values. However, if that index, that little index on that radical, if that's an even value, then it's continuous only when x is non-negative, meaning x is greater than or equal to 0. It could be 0 or it could be a positive, but only for non-negative values can we say that this one's continuous. And if you think about the square root function, just real quick, the square root function is defined only from 0 on, whereas a cube function is defined everywhere. And so that kind of helps with that. All right, a few other functions. E to the x is continuous everywhere, as is the natural log of x. Those are inverses of one another, so those work nicely. Sine and cosine functions are continuous everywhere. Now, tangent, the cotangent, secant, and cosecant functions, they are continuous everywhere they're defined. However, they do have some vertical asymptotes, so that is where they would be discontinuous. And that might help, I'm hoping. So there you go, a few things on continuity. Enjoy.